Hello everyone and welcome to Calc Lesson number 50. Today we are going to be reviewing some topics that you covered last year in pre-calc. We're going to start with a review of sequences and series, and then we will move on to a review of summation and sigma notation. So we're going to start with some basic pattern recognition. For each of the sequences below, we want to find the next three terms. So we're going to look at each sequence, try to identify the pattern, and then from there list the next three terms. So take a second, look at numbers 1 and 2, pause the video if you need to, see if you can identify those patterns, and then come on back and we will go through it together. So for number 1, hopefully you recognized your pattern as adding one more each time. So from 1 to 3, you added 2. From 3 to 6, you added 3. From 6 to 10, we added 4. From 10 to 15, we added 5. So to list out our next three terms, from 15 to the next one, we would add 6. So 15 plus 6 gives us 21. Then we would add 7. So 21 plus 7 takes us to 28. And then we would add 8. So 28 plus 8 takes us to 36. So the next three numbers in our sequence would be 21, 28, 36. For number 2, again, take a second if you need to recognize the pattern. For each of these, we are multiplying by 2. So to find our next three terms, we would do the same. So 64 or negative 64 times 2 takes us to a negative 128. Multiplying by 2 gives us the term negative 256. And multiplying by 2 takes us to negative 512. So the next three terms in this sequence would be negative 128, negative 256, and negative 512. So for the next couple, we're still looking at a sequence. This time we're going to be finding the first three terms where we're given the pattern. So we're given a sub n. And we want to find the first three terms, so when n equals 1, 2, and 3. So for our first one, for number 3, when a equals 1, we would have 3 times 4 to the 1 minus 1, which gives us 3 times 4 to the 0. 1 to the 0 is just 1, so our first term would be 3. 3 times 4 to the 2 minus 1 gives us 3 times 4 to the first, and 3 times 4 is just 12. And then our third term, 3 times 4 to the 3 minus 1, gives us 3 times 4 squared. Remember your order of operations, you would do 4 squared first, so 3 times 16 gives us 48. So the first three terms in this sequence, 3 times 4 to the n minus 1, would be 3, 12, 48. For number 4, same thing. The pattern, the sequence we're given here is a sub n is equal to negative 6 over n plus 3, and we want to find the first three. So when n equals 1, 2, and 3. So if n equals 1, we have negative 6 over 1 plus 3, gives us a negative 6 over 4, or a negative 3 halves. When n equals 2, we have negative 6 over 2 plus 3, which cannot be reduced and is just left as negative 6 fifths. And then when n equals 3, we have negative 6 over 3 plus 3, which gives us a negative 6 over 6, or a negative 1. So our first three terms in this sequence would be negative 3 halves, negative 6 fifths, negative 1. Now for number 5, we're doing the same thing. We're still finding the first three terms in the sequence. This one's a little bit different because our pattern is a sub n equals 3 times a to the n minus 1. So a to the n minus 1 is referencing your previous term. So then they have to give us that our first term, when n equals 1, a sub 1 is equal to 2. So our first term here is going to be 2. Our second term, when n equals 2, would be 3 times a to the 2 minus 1, which is 3 times a sub 1, which is 3 times, and then a sub 1 was 2, which is just 6. And then when n equals 3 for our third term would be 3 times a, and then this would be 3 minus 1, gives us 3 times a sub 2, which is 3 times what we found as our second term, which is 6, which gives us 18. So this sequence relies on your previous term. Using the given a sub 1 is 2, we find our first three terms to be 2, 6, 18. So a quick review of sequences for you. So for the next couple, we're going to write each series as a sum of terms, and then we're actually going to go ahead and calculate that sum. So it's just a quick review of sigma notation. Your sigma is that big squiggly E. Remember that this n equals 1, that is going to be where we start, or our first term. And then this 4 is going to be our final term, or where we end would be when n equals 4. So we're going to go ahead and plug in 1, 2, 3, and 4. And because we're writing them as a sum, we're going to add them all together. So let's start by plugging in n equals 1. We get 20 minus 1 squared. 20 minus 1 squared is just 19. We're also going to plug in when n equals 2. So we have 20 minus 2 squared. 20 minus 4 is 16. When n equals 3, we get 20 minus 3 squared. 20 minus 9 is 11. And then when n equals 4, our last term, we get 20 minus 4 squared, and 20 minus 16 is just 4. Because this is sigma notation, we're going to write it as a sum, meaning we're going to add all of these together. So 19 plus 16 plus 11 plus 4. Grab your calculator or do that in your head. 19 plus 16 plus 11 plus 4 just gives us 50. So the sum from when n equals 1 to 4 of 20 minus n squared is just equal to 50. So this is a quick review of sigma notation and how to write your series as a sum of terms, and then actually go ahead and calculate that sum. Okay, for number 7, the same thing. We're going to calculate the sum from when n equals 1, from when n equals 1 until n equals 4 of the quantity n plus 600. So we're going to plug in for n equals 1, n equals 2, n equals 3, and n equals 4, and then go ahead and actually calculate the sum. So we have 1 plus 600, which is just 601, 2 plus 600, which is just 602, 3 plus 600, which is just 603, 4 plus 600, which is just 604. Because it's a sum, we're going to add them all together. So 601 plus 602 plus 603 plus 604 all together gives us a sum of 2,410. So the sum from when n equals 1 to 4 of n plus 600 is just equal to 2,410. Okay, and for number 8, we're not doing anything different. Here we have the sum. This time we have a different variable from when k equals 1 until 6. We're going to do the same thing, just with a different variable of 300 over k. So we're going to start at 1, k equals 1, and we're going to plug in all the way up until k equals 6. Plugging into our formula, so we have 300 over 1, 300 over 2, 300 over 3, 300 over 4, 300 over 5, and 300 over 6. But let's go ahead and reduce. 300 over 1 is just 300. 300 over 2 would be 150. 300 over 3 we can reduce to 100. 300 over 4 is just 75. 300 over 5 would be 60. And 300 over 6 would be 50. Again, this is a sum, so we are adding these all together. And when we do that, 300 plus 150 plus 100 plus 75 plus 60 plus 50, we get 735. So we can write the sum from when k equals 1 to 6. 300 over k is equal to 735. So a quick review of sigma notation and how you actually calculate a sum when given sigma notation. If you have any questions, you can ask your teacher to pause the video and to go over these first few examples before we move into our next topic. So these next couple are a little bit different because now we're going to be given the sum of terms like we were finding in the last couple of problems, and we're actually going to write it using sigma notation. So we're going to be looking for a pattern, determining our start and our ending value, and then writing it as a formula. So here's the example. We have 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. When we look at that, I notice that the 1 is always the same. It's consistent. The thing that is changing is the value in the bottom. Because it's just adding by 1, I know I'm going to start with my first term as n equals 1, or in this case, because we're going to label it with a k, as k equals 1. So this would be 1 over 1, and then I can make that adjustment for each one. For each term, I know that it would just be 1 over whatever term that is. So we can write this as the sum using a sigma, starting with our first value when k equals 1, and then our last term happens when k equals 5, and then we write the pattern just as 1 over k. So we're going to try the next couple together. So for number 9, we have the sum 1 plus 4 plus 9 plus 16 plus 25. These are all special numbers. In fact, these are all perfect squares. So I'm going to think of this as 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And if I can rewrite it so that I see the pattern as each one being something squared, my first term I'm going to let be n equals 1. That makes my last term n equals 5. So we can write this pattern as the sum, sigma, starting when n equals 1 and going until 5. And then to write this pattern using an n, because the n value is what's being squared, we can write this as n squared. So sigma, the sum from when n equals 1 until 5 of n squared. For number 10, again, we want to take that sum of terms and write it using sigma notation. So here we have 5 plus 10 plus 15 plus 20 plus 25 plus 30, and something these all have in common is that these are all multiples of 5. So I'm going to rewrite this as multiples of 5. So this would be 5 times 1 plus 5 times 2 plus 5 times 3 plus 5 times 4 plus 5 times 5 plus 5 times 6 would give me 30. So because these are all multiples of 5, now that I've taken that 5 out, I see my n values 1, 2, 3, 4, 5, and 6. So starting when n equals 1, and this time going until n equals 6. So we can write this as the sum, sigma, from when n equals 1, this time ending at 6. And then we want to write the pattern and just replace those 1, 2, 3, 4, 5, 6 with an n. So this would be of 5n. So just a little practice writing your sum of terms in sigma notation. Take a second, review, ask any questions, and then we're going to try 2 more together. Okay, the next 2 are similar, just a little bit trickier. So for number 11, we have 1/3 plus 1/9 plus 1/27 plus 181. And again, our goal is going to be to write this using sigma notation. So just like in the example, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, that 1 in the numerator I can count on as being consistent. So what I really want to focus on are the numbers 3, 9, 27, and 81. Hopefully you recognize each of those as multiples of 3 and even more than that, powers of 3. So if we rewrite these terms as a power of 3, we have 1 over 3 to the first, plus 1 over 3 squared, plus 1 over 3 cubed, plus 1 over 3 to the fourth. So now that we can write these as 1 over 3 to some power, starting, let's use k, when k equals 1, going all the way until k equals 4. We can write this sum as the sum, sigma, from when k equals 1 until 4, and the pattern here is 1 over 3 to that kth power. Now number 12 is a little bit different. We have 1 over 2 plus 2 over 3 plus 3 over 4 plus 4 over 5 plus 5 over 6. And I bet if this pattern were to continue, you could guess the next couple of terms. What's happening each time is our denominator is kind of moving over to the top of the next, to the numerator of the next value, and the numerator and denominator of each fraction are related closely by 1. So let's try a couple of things, and let's let our first term be n equals 1. So let's write this as 1 over, and then our denominator is just 1 more, 1 plus 1. In our second term, if n is equal to 2, we have 2 over just 1 more than that, 2 plus 1. When n equals 3, we have 3 over just 1 more than that, 3 plus 1. So if we write this using sigma notation, we're starting here when n equals 1, and we're going up until 5. And then to write this as a series, or to write this as a sigma notation, we're going to use our n value in our numerator over 1 more than that in the denominator would be n plus 1. So just a little bit of practice taking your sum of terms and rewriting it as a series in sigma notation. So just as a summary of kind of what we've been practicing and some formal vocabulary review, sigma notation, the sum of n terms the sum of n terms, a sub 1, a sub 2, a sub 3, all the way up to a sub n is written using sigma notation as such. And then a little bit of vocabulary review. This letter I is known as your index of summation. And that's sometimes I or J or K. The 1 is called your lower bound. And then n is your upper bound. And then just a note that I does not have to start at 1, but it does matter if it doesn't. So we're going to be looking closely at whether it's starting at 1 or not in the next couple of examples. All right, so we're going to begin with a couple of easy examples, and I'll just put those easy in quotes. And when we call them easy, I mean the values are small enough that we can just go ahead and add them. So for the first one, we have the sum from when I equals 1 until 6 of, and then our formula here is just I. So if we plug in I equals 1, we have 1, plus when I equals 2, we have 2, plus when I equals 3, we have 3, plus when I equals 4, plus when I equals 5, plus when I equals 6. So these are small enough values that we can go ahead and just add them, or you might recognize there's pairs, 6 and 1 are 7, 5 and 2 are 7, 3 and 4 are 7, so we can also think of this as 3 times 7, and our sum here would just be 21. And then same thing for number 2. Take note, here we have the sum from when I equals 3 until I equals 7, so here we are not starting at 1. So starting when I equals 3, we would have 3 squared, which is 9, plus 4 squared, which is 16, plus 5 squared, which is 25, plus 6 squared, which is 36, and then we're ending here at 7, so plus 7 squared, which is 49. Again, small enough values that we can just go ahead and add these. And adding 9 plus 16 plus 25 plus 36 plus 49 just gives us a sum of 135. So just a couple quick, easy examples before we move into some of the more complicated and more fun examples. So we're going to look at some more fun examples of summations with sigma notation, but first there's just two properties that we want to look at. The first is if we have the sum from when I equals 1 until n of k times a sub I, and k is our constant, then you can actually bring that k out to the front and then find your sum from when I equals 1 till n of a sub I with your constant out front. So that's our first property. The second property is if you have the sum from when I equals 1 until n of a sub I plus or minus b sub I, you can actually split up those two summations. So you can have the sum from when I equals 1 until n of a sub I, and then add or subtract the sum from when I equals 1 until n of b sub I. So two important properties to know as we move into our more complex examples. Okay, and then before we get to those fun examples, you have some important summation formulas. So if you can recognize one of these four formulas, then there's no need to do a sum of terms and actually calculate it. You can jump to one of the four formulas below. Just a quick note before we go over them is that all of these have I equals 1. So if you don't have I equals 1 in the problem you're trying to solve, then in order to use one of these formulas, you need to then add or subtract the extra piece. And we'll go through a couple like that in a minute. So your four formulas, and if you can recognize one of these four, then you do not have to do your sum of terms. You can jump right to your formula. The first one is that if you have the sum from when I equals 1 to n of c, where c is a constant, just a regular number, then that is just equal to c times n, where n is that upper bound. Your second important formula to notice is if you have the sum from when I equals 1 to n of I, then you don't have to do the sum of terms. You can jump to your formula that this sum is equal to n times n plus 1 over 2. The third is the sum from when I equals 1 to n of I squared, and that's equal to n times n plus 1 times 2n plus 1 all over 6. And then finally the sum from when I equals 1 to n of I cubed, and that's equal to n squared times n plus 1 squared over 4. Again, these are four important formulas that if you can recognize, you don't have to do your summation of terms. You can just jump to your final formula. Your teacher will give you these, so she's probably already posted it for you under content library or wherever she usually posts important formulas and formula sheets, so make sure you have access to this, and if not, maybe you just pause the video and take a quick screenshot so that you have this for the rest of today's lesson and the lessons to follow. Okay, so we're going to work through a couple together using both the properties and the formulas, so make sure you have those nearby. Number one, we're looking at the sum from when I equals 1 until 10 of 4. 4 is just a constant, so we can go ahead and use that formula. The sum from when I equals 1 to n of c is just equal to c times n. So before we jump right in and use it, let's first confirm that we start at I equals 1, and we do, so we can go ahead and move forward. Looking at our formula, let's identify our n value as being equal to 10 and our c value as being equal to 4. Following the formula, the sum from when I equals 1 to n of c is just equal to c times n. We can set this summation equal to c, which is 4, times n, which is 10. so this summation is just equal to 40. And if you don't believe me, you can go ahead and try it. The sum from when I equals 1 to 10 of 4, well, you would plug in an I for every term between 1 and 10, but because there's no I value, you would just be adding 4 plus 4 plus 4 10 times, or 4 times 10, and you would get 40. For number 2, we have the sum from when I equals 1 to 20 of 3 times I. Because 3 is a constant, we can start with the property where you can take your constant k and move it to the outside. So let's start by rewriting this as 3 times the sum from when I equals 1 to 20 of I. With our 3 on the outside, we can now just focus on this summation. And now that we have a summation of just I, we can use another formula, the sum from when I equals 1 to n of I, and that's going to be equal to n times n plus 1 over 2. So again, just a quick visual scan to make sure we're starting at I equals 1, which we are. That makes our n value equal to 20 in this case. So we can bring our 3 with us, and then finding that sum, the formula says this is going to be equal to n, which is 20, times n plus 1, so 20 plus 1 is 21, all over 2. And from here we can just simplify. So this is going to be equal to 3 times 20 times 21. So let's do 20 times 21 divided by 2. So 20 times 21 is 420, divided by 2 is 210. So 3 times 210 is just 630. So numbers 1 and 2, using those first couple of summation formulas. If you have any questions, go ahead and ask your teacher to pause the video. All right, for number 3, we have the sum from when I equals 1 to 10 of I squared minus 1. So let's start by using the property that when we are adding or subtracting two terms, we can actually split up our summation. So let's split this into the sum from when I equals 1 to 10 of our first term, which is I squared, minus the sum from when I equals 1 to 10 of our second term, which is 1. So now we have two separate summations that we can work with. So let's start by working with the first one, the sum from when I equals 1 to 10 of I squared. Doing that, we can use our formula for I squared. Again, a visual scan, make sure I is equal to 1, which it is. That makes our n value equal to 10. So we can start by completing this summation as our n value, which is 10, times n plus 1, so 10 plus 1 would be 11, times 2n plus 1, so 2 times 10 is 20, plus 1 would be 21, and that's all over 6. And then we're going to subtract, and then the summation from when I equals 1 to 10 of 1, well, 1 is just a constant c. So again, a quick visual scan, make sure we're starting at 1, which we are. Our n value here is going to be equal to 10, and then our c value is equal to 1. So this summation is just equal to c times n. C is 1 times n, which is 10. So now we can go ahead and simplify. So 10 times 11 times 21, 10 times 11 times 21 gives me 2,310, and then we divide that by 6, and we get 385, minus 1 times 10 is just 10. So this summation, the summation from when I equals 1 to 10 of I squared minus 1 is just going to be equal to 375. So just as a recap, we didn't have to go through and plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then add them all together. We were able to use the property where we could split up our two summations and then use two separate formulas to come up with our final answer of 375. Okay, so numbers 4 and 5 are going to be a little bit different. We're still looking to find our sum, and I put our formula for the sum of I in the upper corner so we could reference it. However, when we go to start with our visual scan, we're looking to confirm that I equals 1, and in this case, it does not. So because it does not equal 1, we have to actually start or we can only use formulas where I does equal 1. So here we have to supplement. So we're going to start by finding the sum from when I equals 1 to 20 of I. And that's almost what we want, but we wanted to start counting at 5. So when we start at 1, we're accidentally counting 1, 2, 3, and 4, and we don't want to include them. So then we have to subtract the pieces that we don't want, and we want to exclude the sum from when I equals 1 until 4. So because we only want it to include starting at 5, we're going to get rid of the sum from when I equals 1 till 4 of that very same formula I. So now we have two separate summations. In our first summation, we have I equals 1, so now we're good to use the formula. And in this one, n is equal to 20. So plugging into our formula, this is equal to n, which is 20, times n plus 1, which is 21, over 2. And then we're going to subtract, and we can use the summation formula for the second piece, again confirming that I equals 1, so now we are good to go. In this case, n equals 4. So using our formula, we have n, which is 4, times n plus 1, which is 5, over 2. Simplifying, 20 times 21 is 420 divided by 2 gives me 210, minus 4 times 5 is 20 divided by 2 is just 10. So this summation from when I equals 5 to 20 is just equal to 210 minus 10, or just 200. So if you added up every number between 5 and 20, 5, 6, 7, 8, 9, 10, all the way up to 20, you should get 200. And then for number 5, we have the sum from when I equals 3 till 10 of I cubed. We run into that very same issue here. Here we have I equals 3, which is not I equals 1. Why can't I highlight this? Which is not I equals 1, so we have to supplement. So why don't you guys pause the video and see if you can set it up, and then come back and we'll check it over together. So in order to supplement here, hopefully you wrote this as the sum from when I equals 1 till 10 of I cubed, and then we're subtracting or taking away the sum from when I equals 1 until 2, because we want to start counting at 3, and again of I cubed. So now we have two summations. The first one starting at 1, so we're good to use the formula in the top right corner. In our first summation, we have n equal to 10. So using our formula, we have n squared, so 10 squared, times 10 plus 1, which is 11 squared, all over 4. And then we're going to subtract. And using our formula for our second summation, again, we have I equals 1, so we're good to use the formula. This time n equals 2, so we have n squared, which is 2 squared, times 2 plus 1, which is 3 squared, all over 4. 10 squared times 11 squared divided by 4, we should get 3,025, minus 2 squared times 3 squared over 4, we should get 9. So the summation from when I equals 3 to 10 of I cubed is equal to 3,016. And again, if you were to add up all of the cubes starting at 3 and ending at 10, you should get 3,016. Okay, the last type of example we're going to do is we're going to look at the sum of terms, and we're going to use sigma notation to write this as a sum. So here we have 9 over 1 plus 1, plus 9 over 1 plus 2, plus 9 over 1 plus 3, and then dot, dot, dot means we're going to go all the way up until 9 over 1 plus 14. So notice in each of these terms, the 9 is the same, and the 1 is the same. So just like we were doing earlier, if we let our first term be n equals 1, or in this case, let's write it as I equals 1, then this would be I equals 1, I equals 2, I equals 3. We're going to go all the way up until I equals 14. So we can write this as the sum from when I equals 1 up until 14. And then we're keeping our 9 and our 1 plus is always the same. And then what we're plugging into each one is that 1, 2, 3, 4. So we can plug that in as an I. So we can rewrite this as the sum from when I equals 1 to 14 of 9 over 1 plus I. Okay, and for number 7, we're doing the same thing. So why don't you pause the video, go ahead and try it, and then come on back to check. Here we want to write sigma notation for the sum of 1 over 3 plus 3 times 1 plus 1 over 3 times 2 plus 1 over 3 times 3 all the way up until 1 over 3 times 10. Just like in the last one, our 1 is constant and so is our 3. What's changing is this 1, 2, 3. So let's start at I equals 1 and we're going all the way up until I equals 10. So we can write this as the sum from when I equals 1 until 10 of 1 over 3 is all constant, and then we are just multiplying by our I value. All right, guys, I hope this review was helpful, reminded you of some of the summation and formulas and sigma notation that you used last year in pre-calc. Homework 50 is just a couple of problems from the book to practice using this notation and finding these sums before we start using them for real in our next lesson. As always, if you have any questions, you can reach out to your teacher. We'll see you next time.